Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
NASA just warned Voyager 1 just made an impossible discovery deep in space. The message crackled through mission control at JPL, and for a moment even the veteran engineers holding decades of experience felt a jolt of disbelief. Voyager 1, humanity's farthest-flung ambassador, had transmitted data unlike anything ever recorded, signals that defied the established laws of physics and hinted at phenomena so exotic they challenged the very foundations of our understanding of the cosmos. Before we start, hit the like and subscribe buttons for more exclusive news. The discovery began, as many path-breaking moments do, with routine monitoring. Voyager 1's instruments, painstakingly designed in the 1970s, continue to relay measurements on magnetic fields, cosmic rays, and plasma waves from well beyond the heliopause, where the sun's influence wanes and the interstellar medium holds sway. On May 14th, the probe's plasma wave subsystem detected oscillations at frequencies that oscillated, not in predictable patterns but in sequences that wound backward through time, as if the waves were traveling in reverse. At first, data analysts suspected a glitch in the aging hardware. After all, Voyager 1 has braved 48 years of cosmic radiation, temperature swings, and micrometeoroid pings. Yet cross-checks against redundant sensors confirmed that the readings were genuine. As the realization sank in, teams compared the anomalous signals against every conceivable model. Nothing fit. The frequencies, measured in kilohertz, shifted in a non-linear chirp that violated the dispersion relations governing plasma waves. The patterns implied a medium with negative refractive index, a material that until now existed only in theory and in controlled metamaterials on Earth. Moreover, the waveforms exhibited a coherence and periodicity that suggested intelligent modulation, as though someone or something were sending structured messages coded in the fabric of space itself. Night gave way to dawn at Pasadena, but no rest came for the mission specialists tasked with decoding the enigma. Meanwhile, astrophysicists around the globe scrambled to reconcile the implications. If the waves truly traveled backward in time, this could point to a region of space-time with exotic curvature, where causality loops back on itself. The notion of a time reversal bubble had existed in speculative literature, places where closed time-like curves might allow journeys to the past, but no empirical evidence had ever emerged. Voyager 1's data hinted that such a bubble might lie just beyond the solar frontier, perhaps woven by the shock of the termination shock or sculpted by interstellar magnetic eddies. The possibility of encountering a relic of the early universe frozen in a temporal vortex tantalized theorists, suggesting that fragments of space-time topology long since dissolved could persist at the edges of our stellar neighborhood. But the implications ran deeper still. Negative refractive index in free space would upend Maxwell's equations as applied to the interstellar medium, demanding a wholesale revision of electromagnetic theory under extreme conditions. Spacecraft communications, which rely on predictable propagation through plasma, might become impossible in such regions, raising questions about the future of deep space exploration. If pockets of bizarre physics lurk between the stars, probes and sensors would need new hardware and algorithms to navigate and interpret data. The techniques that carried Voyager 1 unerringly for nearly half a century might be obsolete for the next generation of interstellar Voyagers. Speculation mounted quickly. Was the anomaly natural or artificial? The structured nature of the signals, regular spikes, phase shifts, and amplitude modulations, mirrored patterns one might design for interstellar messaging. SETI researchers, long accustomed to skimming radio sky surveys for unexplained narrowband carriers, found themselves turning to Voyager's plasma wave records, suggesting that intelligence might not only be broadcasting in the electromagnetic spectrum, but embedding information in the plasma itself. Could an alien civilization, recognizing the silence of the void, harness the very medium of interstellar space to cloak its transmissions? Or had Voyager stumbled upon the remnants of a long-dead engineering project from a bygone epoch, now adrift among the cosmic currents? Engineers at Mission Control faced a stark dilemma. Voyager 1's technical architecture could not be reprogrammed to isolate or filter the anomalous waves. The probe's software and hardware are fixed, with no possibility of in-flight modification. All that remained was to apply advanced post-processing on Earth, deconvolution algorithms, machine learning-driven pattern recognition, and cross-correlation across decades of archived telemetry. Teams pored over petabytes of data, seeking faint traces of the anomaly's onset. Was this phenomenon emerging suddenly beyond 150 AU, or had earlier hints been buried under noise floors? Early indications suggested that the impossible discovery had roots as far back as 2018, but only now had the noise suppression and data smoothing techniques matured enough to reveal the pattern in full clarity. Public reaction was immediate and intense. Amateur astronomers tuned radio telescopes to the same frequencies, hoping to catch a glimpse of the anomaly from Earth's vantage point. Journalists pounced on the phrase, time reversal signals, evoking images of wormholes, parallel universes, and cosmic conspiracies. Social media buzzed with speculation, as influencers declared the discovery proof that mankind was not alone in the universe, either visited by alien engineers or on the cusp of unlocking new dimensions of reality. Space policy experts, however, cautioned against sensationalism. One respected commentator noted that, before we talk about warp drives and temporal loops, we must rigorously exclude every mundane explanation. Instrumental artifacts, solar wind interactions, or local interplanetary dust effects. Within academia, the discovery galvanized research efforts across multiple disciplines. Plasma physicists proposed experiments to recreate the observed negative index effects in laboratory conditions using dusty plasmas and magnetized flows. Mathematicians dove into the Einstein field equations, exploring solutions that might permit self-consistent causal loops stabilized by exotic matter. Philosophers of science debated the epistemological implications of encountering data that defy existing frameworks. Would science expand its methodology to encompass nonlinear causality, or reject the anomaly until a more conventional explanation emerged? Space agencies beyond NASA took notice as well. ESA officials quietly reviewed their records from the Ulysses and Cassini missions, seeking similar anomalies in ultraviolet and radio wave data. Japan's space agency considered adjusting the trajectory of its Akatsuki probe to swing through the same region of interstellar space, hoping to offer corroborating measurements. Even private space ventures, long focused on near-Earth commercialization, began to envision missions that could shuttle dedicated probes into the uncharted fringes. Investors, sensing a paradigm shift, eyed opportunities to fund next-generation instrumentation capable of probing beyond the heliopause with unprecedented sensitivity. Meanwhile, Voyager 1, its power supply waning yet still transmitting, drifted onward into the darkness. The longevity of its radioisotope thermoelectric generators, feeding at ever-decreasing wattage, had always posed a ticking clock. If the anomaly persists, mission planners will need to decide how to prioritize limited resources, maintain the full suite of instruments and risk losing contact sooner, or focus power on the plasma wave subsystem to extract every possible bit of information from this cosmic puzzle. The choice underscores the tension between continued routine science and the quest to unravel an impossible discovery that may rewrite textbooks. Among the broader scientific community, debates raged over publication and peer review. Should the initial findings be presented at the upcoming American Geophysical Union Conference, even as data processing continues? Or held back until multiple lines of evidence could confirm the anomaly's persistence? The cautious scientific impulse favored methodical verification, but the public's insatiable appetite for drama urged a faster reveal. Behind closed doors, principal investigators weighed the risk of being scooped by preprint servers against the imperative of collective scrutiny. Ultimately, they opted for a preliminary report in a reputable journal, with data repositories open to qualified researchers under controlled access. At the heart of the implications lies a profound philosophical question. What does it mean for humanity if our theoretical frameworks prove insufficient? Since the revolution of quantum mechanics and relativity, science has periodically faced moments where experiments confront the unknown and demand new paradigms. The Voyager 1 anomaly may represent one such inflection point, where reductionist models yield to a more holistic view of space-time, information, and matter. It suggests that the cosmos still harbors corners where human imagination must expand, inventing new mathematical languages and experimental techniques to grasp nature's subtleties. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on Voyager 1's impossible discovery? We want to hear from you. Thank you for watching, and see you next time.